May I have your attention, please? All right. Today I would like to talk about, please be quiet. I'm going to talk about, well, finally, objects. Today you will learn precisely what do we mean when we say acceleration of the object, and why is it that I suggested that if we approximate object by a particle, why did I say that you should think that entire mass of the object is concentrated at the center of mass, and it has, and then we can treat it like a particle. I'm going now formally to introduce concept of center of mass. Probably some of you know how to find the center of mass of object. So, for example, if I support this object just below center of mass, yeah, I can see that center of mass is somewhere along this line. I can also look at this and find out that it's going to be somewhere along this line. It's even better to hang it. Well, in the future, actually, we will learn that really when we look for center of mass this way, we are looking for a different point which happens by coincidence to overlap with the location of center of mass. Really, I would be this way. I mean, by balancing objects, I'm looking for a point which is referred to as, anybody knows? Center of gravity, correct. Center of gravity. When we support it and use gravitational field to balance object, then we are looking for center of gravity. But in a gravitational field like we have in the classroom, so if an object is relatively small so that we can consider that it is in a uniform gravitational field, then the two points overlap. They don't overlap in general. So, for example, center of gravity of the moon due to attraction by Earth does not overlap with the center of mass of the moon. And as a consequence of this fact, at this point we see only one side of the moon because the two centers do not overlap. Well, if we reverse the situation and think about gravitational attraction of Earth by the moon, center of gravity of moon's gravitational gravity on Earth, it does also not overlap with the center of mass of Earth. In result, Earth is spinning slower and slower and slower. We will learn in the future how does it happen. Well, but for small objects, for pieces of machinery, for any actually engineering problem, we can consider that center of gravity overlaps with center of mass, and we could balance objects. I like even this one, this method of finding center of mass. If I now start bringing fingers together, they will meet below the center of mass. Too fast. All right. And we'll find out why does it happen like that. But right now, let's come back to an object. So let's say that we have a certain object. We assign a point to an object which we call a center of mass in this particular way. We have to divide object into small pieces, and for each piece we multiply position of that piece by mass of that piece. We add all those products and divide by the total mass of that object. We will get a vector, and that vector identifies position of the center of mass. So if we introduce coordinate system, now I have to multiply mass of this fragment by position of this fragment. It will give me some kind of a vector, right, in the direction of this vector r. And for each fragment of the object, I have to repeat it. Add all those products, all those vectors, and divide by total mass of the object, and then we will get position of the center of mass. The center of mass is really an abstract point. Mass is not concentrated in center of mass. Mass is distributed everywhere. However, well, we will see that it is very convenient point for analysis of well, what will happen with objects when it is when it interacts with other objects. Well, sometimes we can have if we have a finite number of particles, then rather than dividing it into those pieces, we can just I mean, instead of having this uncountable sum, we can calculate product of mass of individual particle and position of individual particle, add those products and divide by mass of the of all particles of the entire system. Why don't we take a look at two examples? One example when we have indeed 3 particles. And let's find out where is the center of mass of those three particles. 3 identical particles. So each of them has the same mass. Why don't we think that one is located at point 1, 0, 0. 0, 1, 0 is the location of the second, and 0 particle, and 0, 0, 1 is location of the third. Now, is it discrete system or continuous? So in other words, should I integrate or should I add? Add, right, because we have only 3 particles. Now, we would have to think actually that each of those has size 0, right? I mean, so these are not, we shouldn't consider that these are spheres. We should think that they are really points. All right, so what we have to do is divide product, multiply each of the particles by its position, mass of each particle by its position, and divide by the total mass of the system. So total mass of the system will be 3 times mass of single particle. All right, now for those 3 particles, I will have mass of the first particle times position of the first particle plus mass of the second particle times position of the second particle, and the same thing for the third one. Well, we have 3 vectors now. When we can see, when I add those 3 vectors, I will get vector 1, 1, 1 over here, right? And M will cancel. So the result is going to be 1/3, 1/3, 1/3. So center of mass happens to be over there. Now the center of mass actually doesn't have to belong to the system. It's not at the location of a particular particle. Well, it happens now that because particles were identical, it is center of mass is at the, well, kind of geometrical center. But in general, it doesn't have to be the case. If one of the particles was heavier than other 2, then the center of mass will be shifted toward that particle. Let's now take a look at finding location of a center of mass of a uniform rod. And again, you have set an intuition already where it is, because if it is uniform rod, then again center of mass overlaps with the geometrical center of the object. So where would you figure out, where should we find that center of mass? Where do you think that it is going to be? Half the length of that rod, correct. It is only because if the rod is uniform. Well, let's now find out formally how to determine that position. So I will divide. I mean, if it is a thin rod, so actually if I divide it into slices, each of those slices can to be considered that this is tiny tiny fragment. So really, although the picture doesn't show it, think about a rod of the thickness of the x-axis. And we will see in a moment that actually from that we can conclude that the center of mass has to be on the axis as well. So we have to concentrate only on x component of the position of that position. So now mass of this fragment, I will relate mass of this fragment with the size of the fragment. So let's say that its thickness is dx. So if thickness is dx, mass of that fragment is volume multiplied by the density at that location. And since it is uniform, density everywhere is going to be the same. So here I have density times volume, right? Here I have a tiny cylinder. This fragment has the shape of a cylinder, so I have to multiply area of the base of cylinder by the height of cylinder. This gives me volume of the cylinder. If I now multiply it by density, I get mass of this piece. So I got mass of this piece. Now mass of this piece has to be now multiplied by position vector. All right. Now we have to add for all pieces. And well, since I have the x over here, I see that it's the variable. I mean, a variable. Then I can state what limits I should choose. And whenever we decide limits, we have to answer ourselves those three questions. Can we come back to those three questions, which at the time when we last integrated, we thought, yeah, how do we have to choose the limits? Nobody remembers. Well, we have to choose them in such a way that we account for every piece. Don't count any piece twice. And don't count a piece which is outside, right? So, for example, if I integrated from minus L to L, what would be wrong? I would include pieces which do not belong over here, right? Okay. So I will now explicitly calculate that. I didn't have to do it this way, but but that, I mean, because I already said that that it should be obvious that the center of mass is going to be on x-axis. But even if I forgot about, if I didn't conclude that, I can figure out that each of those pieces is I mean, like this piece. Its position is x component is x, y component is 0, z component is 0. So vector R has components x, 0, 0. Right now, when we know scalar components of the integrated function, how do we integrate that vector function? Integrate each scalar component separately. Correct. We integrate each scalar component separately. So this is what I did. I integrate x component, I integrate y component, and integrate z component. Well, density multiplied by A well happens to be equal to the mass of this entire rod divided by the length of the rod. Actually, that quotient is also referred to as a linear density of an object. I could really even here think about that this is linear density, which means mass per length of the object. Do you understand me? Okay. Now I can use fundamental theorem for each of those integrals. So m over L is a constant. I can take it in front. I didn't even do in front of the integral. And then I will have integral from x dx, linear function. What's integral of the linear function? quadratic function, x squared over 2. And now I have to plug in limits, L and 0. So when I plug in L, I will have L squared over 2. When I plug in 0, I will get 0. So I will be left just with L squared over 2. So this is the result of integration of the first scalar component. Now the second scalar component, we will integrate 0 function. What are we going to get? 0, right? And the third is going to be 0 as well. Now I just have to simplify things. I see the m and m cancels. L squared and L squared cancels, and the result is L over 2, 0, 0, 0. This is our result. Are we happy with that? What does it mean? What did we get? Yeah, somehow JD concluded the center of mass is halfway of the rod, because what is? These are scalar components of what? Of the position of center of mass, correct. From the definition of the center of mass, position of center of mass is equal to this integral. So here we found scalar components of the position of center of mass. So center of mass is indeed halfway in the midpoint of that rod. Now, what would happen if the rod were not uniform? Yes, Tyler.
So did you use m over L as a constant and plug L in for x, or I'm sorry, I just kind of missed out on that point. For the L squared over 2, did you just plug L in for x and then use
correct, yeah, because I mean, if we come back over here, how do we use, again, fundamental theorem of calculus? We use indefinite integral, right? So we have this integral from 0 to L of x dx. Well, fundamental theorem of calculus says that we can use indefinite integral, like that one, and plug in the limits,
okay.
right?
Okay, so you use
right. So I mean, if I cover these, what is integral, Taylor? What is integral of this function? X squared over 2. X squared over 2. And in a common notation, actually, we put a line over here which repeats the limits, and it means that we have to calculate the difference with those two values. Right, so it is going to be L squared over 2 minus 0 squared over 2. Right, so we are getting L squared over 2 exactly like what we had on the in here. Okay. So what would be different if the rod were not uniform? Let's say that the density is a linear function of which step would be illegal? No. What Mark said, that we wouldn't get 0 values. Well, I mean, I still think about a thin rod. So a rod which really is like a wire along the axis. Well, that it is heavier on one side than on the other side. Well, we integrated x here, right? So we had to integrate anyway. Yes.
dx wouldn't be uniform everywhere.
What will dx won't be uniform? So where would be the difference? Yeah, that ML. Yeah, Mark pinpointed it at least at the right spot. We would have to integrate that m over L In fact, we couldn't even use M over L. I would have to know how density, because M over L is the product of density times area. That quotient had to be, more precisely, this product now should be a function of X. It would vary of X. So instead of M over L, I would have to put explicit function how density depends on location. So for example, if it is a linear function, if I said I would have to put that it is, let's say, lambda x, where lambda is that proportionality coefficient. Now how about if we do it that way? Yeah, so so let's say that density is a linear function of position, which means that rho of x multiplied by a, well, let's say that it is lambda, which is a certain constant, times x. So actually, where that rod, if this is the distribution of density, where the rod is heavier and where it is lighter? The right-hand side is going to be heavier, or the left-hand side is going to be heavier? The right-hand side is going to be heavier, right? Density on the right at the location L will be Lx. Density at origin will be 0, right? So it will be very light on the left-hand side. Well, so in this case, now we have to integrate a function from 0 to L. Now we will have x dx and lambda x, so which will make lambda x squared. So if I integrate that, I will get lambda and integral of, let's use fundamental theorem of calculus, indefinite integral of x squared is x cubed over 3, x cubed over 3, and I have to plug in limits 0 and L, which means that the result is going to be lambda L cubed over 3. So this is the value of that integral over here. Now I have to divide this expression by the total mass of the rod. Now lambda is related somehow to rod to that m, because that lambda has to have such a value that if I add mass of all pieces, I should get mass of the entire rod, right? Which means that if I integrate this, it should give me mass of this entire rod, right? Because this is the differential mass of the rod, which means that lambda L squared over 2 is equal to m. I integrated again this function. It's a linear function, so I took lambda in front and then use fundamental theorem of calculus and plug in limits. I will get this value, which means that therefore, I can plug in now that mass over here, and this should go here. So in the result, lambda and lambda cancels. Do you see that? Now I have L squared over here, and I have L cubed over there, so it will stay L. I will have 3 in the denominator, and this 2 will go to the numerator. So let's get rid of that. So x component of the position of center of mass is now going to be equal to 2/3 of length. Does it make sense? Consult with each other. Does it make sense that we got 2/3? Consult. Make sure that it should be crystal clear that it makes sense. JD, would you like to justify that it makes sense?
Why does it make sense?
Yeah, does it make sense?
Yeah, it makes sense. I mean, we know that the linear density is increasing as you go to the right of x, so we would expect the center of mass to move to the right as well.
Right, very good. JD says that, well, since on this side the rod is heavier than on that side, the center of mass should be shifted to the right compared to uniform rod. And this is what we got. Now instead, instead of being at the center, it is 2/3 of the length. So center, we got the center of mass would be there. All right. Repeat it again.
Where you have the circle lambda L2.
Oh, you don't see the step? Oh, sorry. I mean, probably I'm too fast then in with. So I will plug in over there. So I will have 1 over lambda times L squared over 2 times lambda times L cubed over 3. All right. Now, can you see that this lambda and this lambda cancels?
Okay, I just didn't understand why you. Okay.
This cancels with this one. Do you see that?
So you took the derivative of 1 over m, which is lambda times x.
What derivative?
Not derivative, the integral of.
Correct. Well, because. Oh, I see.
I got
You got it? Yeah. All right. Yeah. I mean, over here, the thing which I erased. Actually, I related mass of the rod to the linear density, right? Because if I multiply this by dm, not by dx, what does it represent? Not the total, but it represents mass of the small piece, right? So I added all of those, which means I integrated it from 0 to L, added masses of all differential pieces. And then this was the result for the total mass of the rod. All right. Now, there are some useful theorems in finding center of mass. I want to bring up 2 theorems which actually allow one to find out center of mass of an object. One is associated with the symmetry of an object. So let's say that we have an object which is symmetrical about this axis. Now let's find out what is the x component of position of center of mass. X component of position of center of mass would require that we multiply x component of position of each piece by mass of each piece, and then divide the integral by the total mass of the object. Now, if I introduce coordinate system like that, so I pick origin to be here along that axis of symmetry. Now I divide object into pieces in such a way that I find symmetrical pieces. I'm talking about symmetrical objects, so for each piece on this side of the axis, I can find identical piece on the other side and locate it symmetrically about the axis. I mean, that axis of symmetry. All right. So if I multiply now x component of position of this piece by mass of this piece, and add to the product of position of this piece and mass of this piece, because this is what is in the integral. If I add these two, what am I going to get? 0. Right? It's going to be 0. Now I take another pair. Somewhere over there, I find a symmetrical over there. So for every piece on the left-hand side, I can find piece on the right-hand side. So when I add those two products for those two pieces, I will get 0. Therefore, the result is going to be that if I add all those zeros, what am I going to get? 0, correct. So this is going to be 0, which means that x component of the position of center of mass is 0. It has to be somewhere along this line. So if we choose axes of symmetry, we can locate the center of mass. Because now, let's say that this is triangle which has all sides equal, and let's say that, I mean, it's uniform. Can you locate the center of mass of this object then? Use the trick of symmetry again. Yeah, now I can choose axis of symmetry like that. Right, so x will be in this direction, and this is axis of symmetry. I know that the center of mass has to be somewhere along the axis of symmetry, which means, well, it is simultaneously on both. Actually, it is simultaneously even on the third one. I can choose this axis of symmetry, and therefore, center of mass is going to be at that location. So let's take a look at some shapes. If I have a uniform square, where is the center of mass of a square? Tell me what to do. Yeah. Oh, square. I was thinking already about the next example. Tell me what to do. Which midpoint? How to find the midpoint? Let's take two diagonals. All right. So one diagonal, another diagonal, and choose this point. And you are saying that this point is the center of mass, right? What's the argument for it?
Because the square, if you use a diagonal as the midline, the square is symmetrical.
Oh. We said, repeat it again.
If you use the diagonals as the midlines, the square is symmetrical to either side of the midline.
All right. Yeah. So if I take this line, I see that. We see that square is symmetrical about this line, which means that the center of mass has to be somewhere along this line, right? And
for the other diagonal,
do the same along the other diagonal. It's symmetrical about this axis, so it has to be somewhere along this line. Good. Yeah, so it has to be simultaneously on both. It has to be there. How about if I complicate it a little bit and take a square?
should be able to do the same thing. Yeah.
I don't know. It's not that obvious anymore. Anybody has another suggestion? Oh, can you pass the microphone to her?
You could fold it like across this way and from the long way.
Right. So rather than this, how about if we think about these lines?
Yeah.
This one and this one. Now, so definitely it's symmetrical about these two and symmetrical about these two. So it has to be indeed. I mean, it happens that diagonals also go through that point. All right, now how about where is center of mass of a circle? Let's do the same thing for a circle. Where is the center of mass of a circle? The center of the circle. Correct. Now, convince me. Mark wants to convince. Can you pass?
You just put it on the XY axis and then just cut it in half, or
Draw
put
X.
the XY right through the middle.
Okay, let's draw X and Y through the middle. All right. And indeed, we see that now circle is symmetrical about this line. Circle is symmetrical about this line. Well, therefore, center of mass has to be in the center. How about if it is not if I don't take a circle, but a ring? No, like washer, for example, where the washer has a center of mass. also at the center, right? Because we can use the same argument as before. If I take a line like this and a line like this, that ring is symmetrical. Therefore, center of mass is at the center of the ring. Note that center of mass doesn't have to be inside of the object, because right now center of mass is outside of the object. All right, now there is another. The next theorem actually says how to find out center of mass if we have system made from objects for which we know where the center of mass is. So let's say, like, we have this is my object now. This system is my object which I consider. Now for each of those objects it's easy to find the center of mass, right? Because this is a sphere, and let's say that they both are uniform. Where is the center of mass of a sphere? At the center of the sphere. We can use again that argument that the center of mass has to be along axis of symmetry. For this ellipsoid, center of mass is also going to be, well, at the geometrical center, or where the axis of symmetry cross. So it will be somewhere here. Now, for the entire system, well, I can, from the definition, position of center of mass is 1 over mass of the system multiplied by integral of products of position and mass of differential fragments. Now, that I will split that integration into 2, because addition is associative. So I will integrate over one object and then over the other object, and separate those two sums. All right. Now, I can recognize that this integral is equal to product of total mass, mass of that first object multiplied by position of center of mass of the first object. If you don't see it right away, how about if you, where I got it, why don't you take a look at the original equation. So position of the center of mass of the first object requires that I integrate over this object position of each fragment and mass of each fragment, and then divide that by mass of the object, right? So if I multiply both sides now by m1, I will get that mass 1 multiplied by position of the center of mass of object 1 is equal to the integral over the object of product of position and mass of each piece. Yeah, so instead of each of those integrals, I substituted the products. So the position of center of mass of two objects is related to center of mass of each object separately, and actually it resembles something. When I would use this formula for calculating mass of a system, we have already done it today. Can you recall when did we do this? No. The 3 particles. This is what we did for 3 particles, right? So now, actually, if we know center of mass of these objects, we can treat each of the object like a particle and calculate location of center of mass from for those 2 particles. So center of mass of first object can be found from the symmetry property and the second one, and then the middle is going to be here. All right. Now I want you to learn the next version of Newton's second law. How many? What are the first two versions of Newton's second law? Can you repeat it? Can we recall it? First version said net force was equal to mass of the object multiplied by acceleration of the object. This was not the first version of Newton's second law of motion. Chris would... yeah, go ahead, Chris.
The network...
no, this is work energy theorem. So that it is F equals ma, but we have to know what is what of what. What is F, what is m, and what is a in the first version of Newton's second law. Recall that it was for particle. Yes, so first, so F was the net force exerted on the particle, m was mass of the particle, and acceleration was acceleration of the particle. Let me just ask one more thing about which acceleration of the particle. Because you are thinking now, what the hell is he talking about? How many accelerations the particle has? No, there is no concept of total acceleration. Very good. Acceleration in an inertial reference frame. If we choose a reference frame, we will have a particle has only one acceleration. However, depending on this, what reference frame we choose, a particle, I mean, we can make the particle to accelerate any way we want. All right. So the first version was for a particle. And what was the second version? Let me tell you what was the formula. F equals dp over dt. A rate of change in momentum of what? Of a particle, correct? Is equal to the net force exerted on the particle. Now, which rate of change in momentum actually we have to consider? One particle. Yeah, which rate of change in momentum of a particle we have to consider? In an inertial reference frame. Remember that inertiality of the reference frame, please. All right. Now I will think about total momentum of this object, which means, well, object is a system of particles. What do we mean by total momentum? What is total momentum of the object then? Sum of momenta of all particles. All right. Help me with each step then. I'm now trying to relate rate of change in total momentum of an object. Or a system of particles. Where did I get this from? Yeah, instead of having total momentum of the object, I wrote that it is the sum of momenta of individual particles constituting the object. Where did I get it from? From the definition of total momentum. How did I get this step? This step is purely mathematical. Derivative of a sum is equal to sum of derivatives. All right, where did I get this from? I wrote here that momentum, rate of change in momentum of particle I is equal to the sum of forces which remaining particles exert on particle I, plus all external forces, plus the sum of external forces exerted on the particle. I mean, this net refers to external forces exerted on the particle. Where did I get this from? In other words, I wrote over here net force exerted on ith particle. That one comes from, yeah, what law says that the rate of change of momentum of the ith particle is equal to the net force exerted on the ith particle in an inertial reference frame? Second version of Newton's second law, correct. All right. Now, if I add all those internal forces, I'm over here, I has to be different than J. Right? Particle does not exert a force on itself. So objects can do that, yeah, because one particle of the object can interact with another particle of an object. So I'm an object, and I can use one hand to exert a force on the other hand. However, the other hand exerts an opposite force on the first one. So if I add all of those internal forces, I will get 0. So here, this sum is going to be 0, and I will be left with the force, with the sum of forces exerted only by other objects, by external objects. Well, which means that in an inertial reference frame, the rate of change in total momentum of the system of particles, or we can say total momentum of an object, is proportional or is equal to the net external force exerted on this object. So if this object has momentum in this direction and we apply force in this direction, momentum is going to change in that direction as well. So it is going to move along this particular path. So now compare this version of compare this third version with the second version. Third version of Newton's second law with the second version of Newton's second law. Third version refers to what? Object. And second version refers to a particle. Now look for similarities. For a particle we had what? In the second version. What described motion in the second version? No, not the net force. Momentum, correct. What momentum? Of the particle. So momentum of the particle was in the second version. In the third version we have momentum of the object, which means this is a total momentum of all particles constituting that object. Now what do we have in the on the side of interaction in the second version? Net force. What net force? Exerted on the particle. Correct. Now, over here we have what? Net okay. We have net external force exerted on the object. Now, how about if we think about internal interactions in case of a single particle? In the second version, what were the internal forces? None, right? For the particle we cannot have. Particle does not interact with itself. Here, for the object, we can have internal interaction, but it doesn't matter. It really works exactly the same way, like for a particle. All right. Tomorrow we will even see more similarities between particles and objects, and figure out why we approximate objects by the center of mass.